It is actually I'm 3 hours late. I apologize. I was not just double booked, I was triple booked, but I got it done. Actually, I had a code making panel 2 task group meeting. I had a call with our marketing group, and I had a call with some product VPGMs. So we made it happen, and I'm a happy boy because it's Friday, and I hope all of you are happy out there as well because it is Friday. All right, so I just want to make sure that I am good to go, and hopefully you are all out there ready to subscribe to the YouTube channel. Remember, this is what we got going on. To subscribe. Okay. So Q&A Friday. Hey, Nihad. Yeah, we had a busy day today, buddy. And next week is going to be even busier. And then I have the Eastern section meeting starting next week. I'm doing a 70E safe work practices educational piece for a few electrical contractors in person. So I'll be working with that. And then we have the Felix Sandoval, TSDN, Eaton Tech Talks. So and then we have the Eastern section is Friday, Saturday, and Sunday, and then the Western section is Sunday through Wednesday. So I got the Eastern and the Western back to back. It is stuff is happening. So all right, I believe I am live. Yep, I'm out there. I forgot the yellow duck. So my Instagram folks, sorry about that. Okay, so let's do this. I'm going to move some things around, and I've got to find, I have a slide deck that I prepared for Q&A. Let's see. All right, so I have to hit close on that. Oh, man, I'll tell you what, Nihad, Felix, I'm like discombobulated. There we go. Okay, so we already, some of these I already talked about, so I'm going to have to go down through a little bit and find the new questions. So bear with me. Coordinating breakers B1 with B6, we already talked about that. So if you're interested in that question, or do any of the Eaton breakers still have the requirements to brace parallel conductors? We already talked about that one. Esther and Wester will go virtual too. Can you use up, over, and down for higher fault current reduction rated 5KA? We already talked about SCCR, so check out the previous one for that. Current limiting fuses, can we use them? We already talked about this. How does current limiting fuse constructed? We already talked about that. We already talked about the AC units, and I think Nihad, that's where we ended up on the last call. Okay, so selective coordination with tested pairs in fuse applications. One issue with this is, and this is from JW, and it wasn't 2 days ago. It was 2 days ago when I put this in. Hey, Ryan, good to see you, buddy. All right, this is informal Friday. No tie today. Not even my IEI tie. Selective coordination with tested pairs in fuse applications. One issue with this is that many disconnects accept different fuse manufacturers. There's no requirement in the NEC put a label on a disconnect using this method to inform a future service person to replace only with a certain manufacturer's fuse. I think I did talk about this. I'll just touch on it real quickly. So JW, there are no requirements right now that say, there's no requirements in here that say inform future service to replace only with a certain manufacturer. And I would say it's not just the manufacturer, it's also the manufacturer and model number. And that's what's good for the goose is good for the gander. I mean, that's not just a fuse thing. Circuit breakers as well. And circuit breaker either replacing circuit breakers, or if you are looking at the settings. So any of the settings on a circuit breaker, they all are very critically important to make sure that you maintain the selectivity. Now, I do know that in the 2023 cycle, I'm going to take a quick look in TerraView at Article 700 because I believe there were public inputs, and I believe they made some changes to the selective coordination requirements to recognize that when you make modifications, if you make changes in your power system, that you're going to need to make sure you ensure anything that's put in there is selectively coordinated. So I'm just looking for the right section, and I'm feverishly scrolling down to 700.32. Here we go. Got it. Replacements. Where emergency systems OCPDs are replaced, they shall be reevaluated to ensure selective coordination is maintained with all supply side and load side overcurrent devices. So that is going to be new for the 2023 code cycle. And I would agree with you, there's nothing in the code that specifically says this, but I would argue that you probably don't even need that language because you already have the requirement. And if you make any changes in your power system, you've got to make sure you maintain the requirements. That'd be like the interrupting rating on a circuit breaker. There's nothing that says that when you replace a circuit breaker that the interrupting rating has to be higher than the available fault current. And there's no labels that say that. Well, that's true, but do I need that? I have to know that I have to properly apply the solution. So I don't necessarily need to label everything to say that when you replace this, it has to meet the National Electrical Code. If you are on the emergency side, then you do need to make sure that whatever changes you do selectively coordinate, because that is a requirement of the code. So is there any possibility to attend Western and or Eastern sessions virtually? Oh, man. Felix, I wish, buddy. But here's what my plan is there, and I have to get this through past. Here's what I think I'm going to do. I'm the education chair for the Western section, and I'm on the board, and I work with the other sections as well. I think what I am going to do is, Felix, take some of those presentations and schedule those later, and see if we can't do a virtual version of not just the Western section. So what I want to do is I want to reach out to all of the sections to say what materials in their sections did they think were the cream of the crop, were the memorable moments that presented. And I know it's hard because a lot of the material, all the material is awesome, but there's probably those that they think were rated higher by the attendees. What I'm going to try to do is find out what those were across all the section meetings and see if I can't orchestrate on the IAEI's website or the IAEI's YouTube channel presentations of those by whoever it was did that presentation. So Felix, I'm going to try to do that for you. Hey, Amar Gopinath, Gopal, thank you for joining in, Amar, sorry. All right, Ryan. Okay, so I'm just looking in 700.32. Now you're bringing up 620.25. I'm going to go there. 620.25. I probably should not have my paper book. 620.25. Branch circuits and other utilization equipment. Overcurrent devices. The overcurrent devices protecting the branch circuit shall be located in the elevator, machine, or control space. Additional branch circuits shall supply not identified. Other installation equipment shall be restricted to the equipment identified. 620.64. All right, that's okay. See that? We all would have believed you. All right, 62 is selective coordination, where more than one driving machine disconnects supply by the same overcurrent device. Selective coordination will be selected by a licensed professional engineer or other qualified person engaged primarily in the design, installation, and maintenance. The selection of device shall be documented and made available. Well, they all should be documented and made available. And I think if you look, the selection shall be documented and made available. That same language is in each of those. All right, 65. Oh, Signage. Okay, Signagi. You're into Signagi. Signage. Equipment enclosures containing that. I knew there was somewhere, Ryan. Thank you. I was like, I kept looking in 700 because I remember this being debated, and I thought it was in here and I could not remember, and it's in the elevator stuff. All right. JW, I'm glad we revisited this question. Equipment enclosures containing selectively coordinated overcurrent devices shall be legibly marked in the field to indicate that the overcurrent devices are selectively coordinated. The marking shall meet the requirements of 110.21b and shall be and it gives us exact language. Caution, overcurrent devices in this enclosure are selectively coordinated. Equivalent replacements and trip settings are required. So, man, thank you, Ryan. See, this is what it's all about right here. This is what it's all about. Sharing of information. And I know we took a little journey through 620, but that's okay. You're forgiven, Ryan. You're forgiven. So what JW is pointing out here, and he says a label, there are requirements in 620.65, but that only applies to elevators, dumbwaiters, escalators, moving walk lifts, and chair lifts, right? So that's just the requirements in Article 700, 701, 708. And there's another one in here, 640 something. I can't remember what it was, the information technology. Was it 645? There's a selective coordination requirement. So somewhere in the IT stuff, there's a selective coordination requirement. There's no marking requirements. Now, in the, I'm going to put this up here. So in the 2023 cycle, what we're looking at in 700, and you know, they'll be doing this in 701, 708. They're saying where overcurrent devices are replaced, they shall be evaluated. And I remember that language that was on the elevator stuff, 620.65, Ryan. I remember that coming up in panel 13 because it's two different code panels that deal with that, I believe. I'm almost positive. I'd have to take a look. It was at 625, 620. Okay, let's do this. How do you know what code panel deals with these? I'll show you. This is how we do it. www.nfpa.org/70. And we're going to see who owns 620. What code panel governs 620 as opposed to Article 700? And we're going to see if they are the same. We go to technical committees. And if you scroll right here, and I would highly recommend, do not just rely on what's in the front of this book. Because and you'll say, well, why not, Tom? Because all of that is listed in the front of the book. But I'll tell you, there are some articles that are in the front of this book that are not in any of the buckets of code panels. And I have found a few in the buckets that aren't supposed to be there. So the best place for you to go to determine what article or what code panel governs whichever article is right there. You go to committee scope and responsibility, and then you wait. And then what you do is we can scroll down, and we're looking for 620. 620. I thought it was panel 11. I could just do a search, but I just love to scroll. No, it's not 11. Panel 12. There it is. 620. So Article 620 is governed by panel 12. 700, 701, and 708, all of those are by panel 13. So two different groups of people. This is why you might see a requirement in the code, like in this case, you have a selective coordination, and panel 12 said, hey, we want to mark the equipment that these are selectively coordinated. Panel 13 did not. So it's two different sets of eyes, two different reasoning. And I'll tell you why panel 13 didn't. They said that it's already in the language because it says the selection shall be documented and made available to those authorized to design, install, and inspect. So panel 13 did not feel the need to label the equipment. I personally like the concept of the labeling the equipment, but they elected not to do that. So Ryan says he thinks it should be in 240. And I agree with you, Ryan. I think there's value in the signage. And here's the issue with 240. Remember, well, that's a good point. But here would be my only concern, Ryan. 240 is not a labeling; it's an overcurrent protection thing, right? 700 has the requirements for selective coordination, and if you put it, I know it's multiple times, but if you put it in each, then where the requirement is for selective coordination, you have the labeling requirements. Now there are going to, the 2023 cycle is looking at selective coordination requirements for the normal side. Remember, and I think that's in 240 for feeders. I don't know. I'm on the fence on that one, Ryan. I am really on the fence on that one. The only reason I like it in 700, 701, 708, and wherever the requirement is because that's where you're looking anyway for the requirement for selective coordination. So anyhow, that's just my thought. I don't know. Take it for what it's worth. But if you ever wanted to know which code making panel governs which article, then this is where you go to get the most accurate, active information right here. Committees, scope, and responsibilities under the technical committee for NFPA 70. So, and then you can see the members at this same thing. So if you look over here in panel 2, and I got to do this, you will scroll down through here and look at that. She blows, Cupcake Island, Thomas Dimitrovich. And I'm on 10 as well. So you can go and see who the code making panel members are. All right. Perfect. All right, let's put that over here. So this is what the 2023 cycle is looking at, saying, look, if you replace or you make modifications, because that is not a part of 700.32, but they're looking at adding when you make replacements or if you have modifications, additions, or deletions to the emergency system. The emergency OCPDs with all supply side shall be reevaluated. So that's all I have to say about that. All right, so hopefully that helps. And great discussion. And thank you for the 620.65 hint there, Ryan. I knew it was in there, and I could not find it. I couldn't remember where it was. I thought it was resolved. I remember it being resolved on panel 13. I completely forgot panel 12 accepted it. And that is the value of networking right there. I wonder if it would be possible to change the arcing current requirement in 24087 to be calculated as a % of the available bolted fault current. It could possibly be two methods, one being the percentage and the other the more complex calculation. This would be an easier calculation, and it would seem, with enough research, we could safely come to a number that would work in most installations. All right, how would I answer this one? Okay, so here's what we're going to do. So what he's talking about is arcing currents, right? So let's do this. He's talking about arcing currents, and I do have a form that if you are a subscribe to my website, thomasdimitrovich.com, I do have this up there. And the reason I require you, it's not for money. I don't charge. The reason I have that up there is because I just want to make sure I know who has it. It is only for educational reasons. It has nothing to do with actually creating labels or anything like that. So I have a spreadsheet, and if I make any changes, I'd like to make sure everybody has a copy of those changes. So here's my spreadsheet. Now I don't want to scare anybody, but I'm going to do this. I know it's busy, but here's what this does. So let's talk about arcing current. The person in the question said it would be that the arcing current requirement in 24087 be calculated. So let's look at 24087. Now, my concern with 24087 is it just says arcing current. If you understand IEEE 1584, now how do you calculate arcing current? The only method that we have today to calculate an arcing current that is recognized by the industry, agreed upon by the industry, agreed upon by the industry. You know, I had somebody yesterday tell me, I was talking on the phone with somebody out west, and it was around the western section. I was trying to get some registrations, and she says, "You're from Pittsburgh, aren't you?" And I'm like, "Yeah, how'd you know that?" And she says, "I sense the accent." And she said she can hear it a lot more whenever I talk fast. And sometimes I talk fast because I just got so much energy going on, and I try to get this going as fast as that's going, and sometimes this goes faster than that, and sometimes that goes faster than this. So you always got to be careful. But anyway, hopefully I tried to curb my accent. I don't say yins anymore or yins guys. I was a big user of yins guys, but my big one was and that. This and that, you know, this and that. And instead of saying back there, I would say back there or back there. So anyway, all right. But I am going to slow down a little bit. 240.87 says, where the highest continuous current trip setting for which the actual overcurrent device installed in a circuit breaker is rated or can be adjusted is 1200 amps or higher, A and B apply. And in A, it says documentation shall be available to those authorized to design, install, operate, or inspect the installation as to the location of the circuit breakers. And it says documentation shall be also be provided to demonstrate that the method chosen to reduce clearing time is set to operate at a value below the available arcing current. Now, it says the available arcing current. Now, if I go into Article 100, we don't define arcing current. We define, let's see, what do we define? In Article 100, we define what an overload is. We define what a fault current is, but not an arcing fault current. We have a fault current, and what, unfortunately, and this was one of the reasons why I'm not a fan, I wasn't a fan, and I am still not a fan of our definition of a fault current. Because, and here's my argument, you may or may not agree with me, and that's fine. I mean, everybody has an opinion. I'm giving you mine because I got the chair. I've got the floor. Oh, hey, I will send you that password. I got to check. Sometimes it's how you signed up. I'll just double check and I'll get you that link. So fault current says the current delivered to a point on the system during a short circuit condition. So what the code has done and what 70E has done is basically said fault current is a short circuit current. So in my opinion, fault current is any current that goes outside of the path. This is just what I wanted to see in the code, and I don't always get my way. I won't say I never get my way. I don't always get my way. My opinion was fault current is a general term like an overcurrent. A fault current can be an arcing fault current. It can be a bolted short circuit current. It can be a ground fault current. All of those go outside of the normal path. That's what I wanted to see in the code, that fault current was defined as any current outside of the normal path. And then you have fault current, available short circuit current. You have arcing fault current. So you have short circuit and arcing, and then that would align with how we use it in the code. But it didn't go that way. So now I have an arc fault current, which is not defined in the NEC, but where do I calculate that? I use IEEE 1584. But if you read IEEE 1584, you just don't calculate one value of arcing current for any given bolted fault current. You calculate two values of arcing current. You calculate a value of arcing current, and then what in the 2002 version of IEEE 1584, you took 85% of that. I think it was 85%. I'm just going to double check. I either do an 85 or I sometimes erroneously either say 80% when it's really 85%. Yeah, there it is. So it's 85% of the, you calculate arcing current, and remember what we do. How did we come up with arcing current? I'll show you what we did. I'm going to go back to PowerPoint, and actually I'm going to so I'll give you a little insight to new slide. All right, so I'm going to give you a little bit of an insight, and I don't know how I can do this easily. So let's just say this, that we have a lab, okay? And in this lab, we have a structure where we create arcs in a box. Dr. Lee is the professor who he's out of Texas. I can't remember what university, and I don't want to say university because you know how that can be insulting to some people who are who have their alma mater. So I can't remember exactly which university in Texas, and he'll shoot me if he's watching. So what he did was he said, okay, we're going to up this side, we're going to have arcing current. And this is a very, I don't want to say crude way, but I'm going to cut a lot of the detail out. And this is bolted fault current. So up this axis, I have arcing current. Across the bottom, I have bolted fault current. Now, what he did was he said for any given value of bolted fault current value. So let's say that I have this guy right here. And this is, I don't know, we're just going to say this is 50,000 amps. 50,000 amps of a bolted fault current value. He has a box that basically has three electrodes, spaced a distance away, all that jazz. He puts an ignition wire across all three of those. Boom, we close into that, and kaboom, we get a fault. We get an arc flash, okay? And then what he does is he records a data point. He says, all right, there is a data point. So I have one data point. Then what does he do? He says, set it up again. And we get another data point for that same bolted fault current value. And then what does he say? He says, set them up again, rack them again, puts another one up. Whoa. He puts another one up there. And then maybe he does, I don't know, a few more. And they're saying that range like that. So he gets different, because what do we know about arcing? We know arcs, no two arcs, they're like snowflakes. No two arcs are the same. Okay, so I get, for any given value of bolted fault current value, he runs it over and over and over and over and over, and he gets various values of arcing current, and he plots those. So then he says, let's do it again. Let's go to, I don't know, I'm going to move this over because we get the gist of this now. And let's say he says, I don't know, let's say this is 70,000 amps. All right. And he does the same thing now. Because the current went up, the data points went up. And I could move these around. So say it's this way, and then say, I don't know, say this one went way up here and he had a flyer way out there, right? And then he says, okay, let's do another one. We'll CV. And he says, let's do 80,000 amps. And I'm just going to shift all of these up, but they could be at, again, I may do this. Let's do this just to make sure that, some of these are different. And he may say, look, this is, that's sort of what happened there. So now what are you seeing? You're seeing a minimum and maximum for each of these available bolted fault current values. So then what Dr. Lee did is he did this. He says, I'm going to draw a line here. And I am going to, I am going to draw a line here. And I missed a dot. But in any case, you see, he wants the lines to be just above and just below. Now, what he did before in the 2002 version was he just calculated this top line. And let's do this. I'm being a little bit easy here. So it could be that he comes up and comes down and then comes up and then comes down. He may be doing something like that. I don't know. I'd have to look at the raw data, but you get the point. He creates a line across the top. And then what he did in the 2002 version, instead of creating an equation for this bottom line, he just took 85% and mirrored this line, dropped it down 85%. And what he would even tell you is that when he took the 85%, there were some data points where the arcing current was much lower than what it had to be because he didn't get any values of arcing current that low. But because he was just doing 85% to make it easy to, I think it was JW's point, he had a it was much lower. The data point, the arcing current that you would calculate at 85% was much lower than what it actually was. And what does that do? That drives your incident energy up, right? Because you could be in a longer clearing time of your overcurrent protected device. So he tried to make that portion of the equation easy. So what he did this time was he said, no, he said, heck with that. We're getting rid of that, and we're actually going to come up with an equation, and we're going to curve fit that equation to give me a line that goes below those bottom data points and encapsulates the maximum and minimum for those arcing currents, because the arcing current could be as low as or as high as for any one of these bolted fault current values. So that tells me that I have now an equation for two values of arcing current, the higher arcing current and the lower arcing current. And I closed 24087 sooner than what I wanted to. 24087 just says, I got to tape that back in. It was on one of my programs. I ripped it. I was getting really excited. 24087 says that the clearing time is set to operate at the value below the available arcing current. But which arcing current? We don't say. We just say arcing current. And I could not say you are wrong if you use the higher of the two arcing currents. But as an engineer, I know I would have to use the lower of the two arcing currents because that will give me a longer clearing time. Capiche? So, I need to get a coffee. Hopefully you guys have coffee out there. It is 3:34. And hopefully you're getting something out of this discussion. Just saying. All right. So now, what this submitter, geez, I just got off a code panel meeting. What this person, JW, was asking was, why don't we just create, like, take the bolted fault current value and take 35% and use that number. Make it easy. And to an extent, he's right. I mean, you could say, let's go back to his question. I want to make sure I get his question right, because I started this thinking I don't like it. Hey, Shade 684. I started thinking, Shade, that I don't like his idea, but now I'm starting to come around to it because, and here's my point. I got to find my presentation. I got to find that slide again to find his question. So give me a second. Is that LinkedIn? Q&A Friday. There we go. Jeez. Q&A Friday. I don't know about you guys. I like Q&A Friday better than, and I didn't do a Tuesday and Thursday session because I'll tell you what, quite frankly, I am El Swampoed. Oh, it's right here. I didn't have to do that. It's right here. Selective coordination with tested pairs infused up. No, that's not it. There it is. Wonder if it would be possible to change the arcing current requirement to calculate it as a % of the available bolted fault current. Hey, Greg Brassiere. Hey. Name is from my 97 AOL. Oh my goodness. AOL, America Online. I can still hear that. Hey, good to see you, Greg. So here's the thing. On this one here, okay, let me go. Now I know why. Now I remember why I called my slide okay. All right. Before we even try to come up and make something generic for arcing current, you got to understand what impacts, what are the parameters in and of a piece of equipment that impact the maximum and minimum arcing currents right here, these two values. What impacts maximum arcing current and minimum arcing current? So to give you for instance, I have the key parameters that IEEE 1584 use to calculate incident energy. I have to know my working distance. If I change my working distance from 457 millimeters to 60 millimeters, my energy values, these are all energy. So all of those are energy values, not arcing currents. These are arcing currents. So what you'll notice is I changed the working distance, but my arcing currents don't change because the arcing current is not driven by how close I am to the equipment. What is driven by how close I am to the equipment? How much energy I'm going to experience. So how about the gap between electrodes? Now, what do we know? For a low voltage switchgear, the gap is 32 millimeters. For a shallow, low voltage motor control center and panel boards, 25 millimeters. Deep, low voltage MCCs and panel boards, 25 millimeters. And cable junction boxes, 13 millimeters. So if I take the 25 millimeters and I double it, 50, watch the arcing currents and watch the energy. My arcing currents changed. If I make that 50, if I make it 70, my arcing currents changed. If I make it 25 again, my arcing currents changed. So the gap between electrodes, think about this. Whenever you have what we did in the lab, we create what we call arcs in a box. You have 3 electrodes. I don't have anything that resembles a roll. Yeah, here we go. I got 2 electrodes here. So let's say that these are electrodes. All right. I got 3 electrodes. And what I'm saying in this spacing is this could be 50, this could be 25, this could be 12. It's how far apart these are in my box. So that is my gap in between electrodes. Okay, so I have bars, I'm either this close or that far away, etc. How about the enclosure size, the height, width, and depth? 914 millimeters. Let's say I take the height of this up to 2,000 millimeters. Watch those values of arcing current. When I hit enter, watch the values of arcing current and watch the incident energy. Arcing current did not change. So the size of my enclosure does not play a role in arcing current, but it does play a role in incident energy. So I can take the width up to 5,000. I could take the width down to 20. All right. And depth, in fact, if you even look at the equations, depth only plays a role when it's really, really shallow. So I'm not even going to play with that. So height, width, and depth do not impact arcing current. How about the electrode configuration? What is VCB, VCBB, HCB, and then there's ACB, etc. For outdoors? Let's go back to my pencils. Okay, so if you look at a panel board, I got my IBW Local 8, Toledo, Ohio. I'm going to take that. Forgive me, Toledo. You're now an electrode. Okay, so I have my bus. Okay, so this is my panel board. A panel board bus goes up and down like this. That is VCB. HCB is when my bus is this way. Now my bus is looking straight at me. And what do we know about an arc? Hey, not Harvey Weinstein. Yo, we're learning about arcing currents and arc flash. So what do we know about the arc? If this is my main and my fault is here on the bus, the arc will always flow away from the source. So if I'm looking at a bus and a panel board this way or this way, doesn't matter. I'm looking at the major portion of the copper. My arcing currents will flow down. Or if my main is down here in the bottom, it will flow up. Or if it's this way and my main is over here, it will flow that way. But it flows up and down horizontally, vertically, up and down, left and right. If I have an HCB, which means now I'm looking at the end of the bus. Where would you see that? You might see it in a motor control center. You could see it in a low voltage assembly, depending upon where you enter the equipment. If you're looking at the end of a copper bus, that's the end. Why do we flow away? Is it due to magnetic fields? Yes, it's due to magnetic fields. It's due to current flow. Remember, I have a source, a voltage source. Remember what voltage is? It's a pressure. It's pushing the current through the circuit based upon the impedance of the circuit. So it's flowing away from my voltage source. Think of it like water in a dam. You know, I have a reservoir and I have a dam, and I open up the gates, and it's all flowing away from the pressure, which is my voltage source. So it'll flow away from the voltage source. Good question. So I have current flowing away from the source. I have, if my bus is this way, the energy is flowing down. And then if I'm in an enclosure, it's going to hit the bottom of it and push out. Alejandro, in cubicles, GIS type is it necessary to do an arc flash study? Does it need an arc flash warning label? Ooh, you know what, Alejandro, I think you asked me that question before online, and that's a good question. So here's what I would say, Alejandro. Remember, I've got to think about what the arc flash hazard is. You know what? I'm gonna pick that one up, Alejandro, after this discussion. Okay, so here's what happens. So I got the arc flowing away from the source. So VCBB means if I have my bus this way, if I have an insulated barrier at the end of this bus, then I use VCBB. If I use VCB, as opposed to VCBB, VCB means I have space below this. It's not an insulated barrier. But look what happened when I changed it from VCB to VCBB. Watch the arcing currents. They change. So now in voltage, obviously, if I take this to 208, my arcing currents are going to change. 480, my arcing currents change. So here's the thing. And if you go back to the question at hand, why don't we just do a percentage? And the reason I would say it would be difficult, although I like the idea, it would be difficult because of all the parameters. It depends on the equipment that you're in. It depends on the construction of the bus. It depends on the dimensions of the bus. It depends on if it's this way or if it's this way. It depends on the voltage levels. There are so many different parameters. You would have to have like a table, which I'm not saying that a table is not a bad idea. And I'm not saying, JW, that it is a bad idea. I'm just saying that it would take some thought, and I'm putting my IBW Local 8 back on there. I hope I got it on the right one. Nope, I got it on the wrong one. I put it on IBW Local. Oh my gosh, I can't even read it. I think it's just a generic IBW. This is the local 8. I don't know why they pick red, but they got red. Local 8. All right. I think it would be difficult. I think it could be doable. It would need probably a table, and you'd have to figure out what equipment you're dealing with. But I think it's a challenge. So Alejandro, gas insulated switchgear. When do we do an arc flash study? We have to understand the arc flash hazard. So NFPA 70E tells us we have to do a risk assessment, an arc flash risk assessment. And what do we know about an arc flash? We know there is a likelihood occurrence and arc flash incidents for AC and DC, table 130.5. What I would say is I would look through table 130.5 Charlie in NFPA 70E, because what this will tell you, and it doesn't necessarily, I don't care if it's gas insulated, to tell you the truth. What I care about is what is the voltage that I'm looking at in the exposed conductors. If you, Alejandro, take that gas insulated gear and say, look, the electrical worker cannot open any piece of this equipment and be exposed to anything that could present an arc flash hazard, then no, there would be no reason for a label, because there is no arc flash hazard. If all of the doors open up are low voltage wiring, etc., and we can have the debate on whether or not you can have an arc flash on 120 volts, I would say no, you can't. We don't have any testing or anything like that from an arc flash perspective for a single phase, especially you're not going to have a 120 volt arc flash event. I ain't going to happen. Okay. You'll get a little spark. I mean, an arc flash, you're not going to have anything you're going to have to dress for outside of gloves. You're going to be worried more about shock on 120 volts than anything else. If you've got 480 volts and it's exposed, now you're talking an arc flash event. So Alejandro, I would say, look at your equipment, look at anybody's equipment, and look for exposed conductors. Anytime that you can get an exposed conductor that presents an arc flash risk, then you're going to be into labeling. But if there is no way for somebody to get in touch with anything that can present an arc flash hazard, if everything is insulated, everything is encapsulated, then it would be difficult to say, look, I need to label this because I can expose 480 volts, 4160, whatever the voltage is, outside of 120. So I think you really got to look at what is the exposure. And if you can get a voltage that will expose the electrical worker to an arc flash hazard, if you look at this table, well, you can't see it, but if you look at table 130.5 Charlie, estimate of the likelihood of occurrence of an arc flash incident for AC and DC systems, look at that. If you can't come up with a way that you can present an arc flash hazard for a user, then that would be your telltale. All right. All right. I think so that this spreadsheet can give you a little flavor for what are the parameters that can change. Okie dokie. Okie dokie, Shmogi. All right, so let's check this one out. I also think, hey, you're welcome, Alejandro. I also think some of these concerns about incident energy levels on the line side of the service could be more easily dealt with via modifications on the utility side than in the service itself. For instance, the push for separate enclosures for service disconnects and feeder breakers for a service disconnect will be expensive. Edits to NESC. Pushing states to require protected devices on the utility, transformer, secondary, etc. Okay. JW, I'll tell you what he's talking about, and this, in my opinion, 350. So I've got to find. I got it around here somewhere. All I need is a little one-line diagram. So I don't want to make one. So give me a second. Energy documents. It was probably one of my LinkedIn. Let me try Arc Flash. I've got a folder. It's titled Arc Flash, and there's nothing in it. arc flash, arc resistant, Q&A Friday, the TCC. I'm going to do one line. Switching device, documents, single line. Try that. A lot of PDFs. So what he's talking about is you have to understand the concept of the protecting overcurrent protective device, because if I'm working in a piece of equipment, I got to find my single line. Here we go. Sample. These are not PowerPoint. Motor protection. Start PPT. I apologize. I should have read these questions beforehand. Oh, I see why. I had my sights set on something different. There we go. All right. And I'm going to search for one line, right? One line. Let's see. Transformers. Yeah, let me try this one. Okay, here is what he's taught. Here's what's going on. Let's say, for example, this is from a different PowerPoint. So I'm not going to save this, but I want to make sure you see it. So let's say this is my utility transformer. And I have this is serving a panel board. Shape fill, none. How do I do none? No fill. And I'm going to shape outline black, but I'm going to give it dots because it is the... All right. So in this square box is my... In that square box, that's my panel board, say, for example. The incident energy of this equipment, the incident energy is based on the clearing time of OCPD 1 as it relates to the arcing current in, we'll call this... we'll call this panel 1. In panel 1. So for me to determine the incident energy of this piece of equipment, I don't take OCPD 2, which is the main overcurrent device, and determine my arc flash values based upon the clearing time of that device. I have to calculate the arcing currents in this piece of equipment and then go reflect that through the transformer and look at the clearing time for those currents based on overcurrent protective device number 1. So if my arcing currents will respond to overcurrent protective device number 1 quickly, then I will have a low incident energy in panel 1. But normally, because here's the issue, and I don't show it's. Forget about whether or not it's a utility or not. Any transformer in your power system. And I have a program on this and I explain this. And it might even be this program that I just opened. I don't know for sure, but let me just look down through here. It probably is. Yeah, it is. Okay, so there we go. Look, there we go. So, and boy, what's the chances of that, huh? I think those chances are slim to none. Okay, so if I look at the calories here, the calories right there, that 12.7 is based on the arcing current in this equipment and the clearing time of that circuit breaker. Now, why is it 12.7 calories when I have a 175 amp main overcurrent device? Because that 175 amp overcurrent protective device is inflated. Why do I say that? If you go to Article 450, 450 tells me I can go up to 250% on the primary of this transformer. What am I worried about when I pick the primary device on that transformer? I'm worried about inrush current. I'm worried about having a trip curve. I'm worried about that 175 amp circuit breaker that looks like this having an inrush current in the instantaneous region, causing that 175 amp breaker to trip every time I energize the transformer. So what do? I pick a circuit breaker that has a instantaneous pickup where the inrush currents are less than the instantaneous pickup down in that region. That makes life a lot easier for me. So now I don't have to worry about tripping that breaker when I energize a transformer. And there may be other reasons why I go up to 250%. It could be for selective coordination through that, and that's a whole separate discussion in a different PowerPoint, different presentation. But suffice it to say, I am intentionally adding a delay on the primary of that transformer, so my incident energy will be very high. So what's happening in the code and what he's talking about is there is in 230, go back to TerraView. In Article 230, in the 2023 cycle, there is a 230 dot. Oh man, I thought it was. Hold on. 230 dot. Coming up, it's location. I have to expand that, and it's called. I think it's called location. Marking. There's general. Indicating. Location. 230.91. See? There are some things I can remember, and there are some things I can't. Separate enclosures. So here's what the language said. And this is what he's talking about. Services over 150 volts to ground and not over 1,000 volts phase to phase that include fuses rated 1,600 amps or higher, or circuit breakers where the highest continuous current trip setting for which the actual overcurrent device installed in a circuit breaker is rated or can be adjusted is 1,600 amps or higher. The service disconnecting means and overcurrent device shall be selected or shall be located in a separate enclosure from the feeder or branch circuit overcurrent devices. Why? Now, this is focusing on services. So let's say, for example, that this equipment here, I'm going to copy this, Control-CV. Let's say that this is your service. So everything up here, everything here is the utility. So I'm going to do that, and I'm going to dash this. I'm going to make it really, really thick, and I'm going to give it dashes. Okay, so let's say everything above that is a utility. And now I have 12.7 calories. And what do I do about it? So how do I establish an electrically safe work condition? I got to call the utility. I'm not going up on the pole. I'm not pulling my meter, right? I'm not going to do any of that. I'm going to have to call the utility to establish electrically safe work condition. So what this code says is if this overcurrent device here is 1,600 amps or higher, or larger, then I need to put it in its own enclosure outside of where these feeders are. So this is what it's doing. It's mandating this right here. So it's saying, look, if this is the case, If it's 1600 amps, then you're moving that main overcurrent device into its own enclosure. And why do we do that? Because now I can leverage that overcurrent protective device to calculate my incident energy in the first panel downstream of it. What have we done? Think about risk. Risk is likelihood and severity. What is the likelihood that I am going to have to do justified energized work in an enclosure that only has one overcurrent device, and that is the main? The likelihood is low. The incident energy is 12.7, so the severity is high. In that panel board that has all of those feeder breakers, and what I'm showing is one feeder breaker, which, you know, we can get sassy here and show Control CV. We can say these are, you know, there's multiple feeders in here. There could be, you know, 12 overcurrent devices in here. I can have a bunch of overcurrent devices in here. The likelihood of me having to get into this piece of equipment to add a breaker, to do anything, justified energized work, it's going to happen in this piece of equipment. And if I have my main overcurrent device, my protecting overcurrent device on the secondary of that transformer in a separate enclosure, if it's 1600 amps, I know it's going to have an arc reduction maintenance switch on it. It has to have an arc reduction technology. So my arcing current and my incident energy is going to be low at this first piece of equipment. And think about this. Where is that going to be? It's going to be probably right next to this equipment. I can very easily establish an electrically safe work condition. That's the value of this. And in my opinion, it doesn't need to just be at the service equipment. It can be also at the secondary of any transformer in your power distribution system. It doesn't just have to be a 1600 amp breaker. Because look, I'm showing you right here a 400 amp secondary, right? So this is a 400 amp panel. I went from 12.7 calories because I'm relying on 175 amps breaker on the primary of that transformer down to 0.17 because all I did was break out the main. Separate that. Separated in the same panel board qualifies? No. So separated in the same panel board does not qualify, Felix. I would have to pull that out. It says separate enclosure. So, and let's see, is enclosure a defined term? What is an enclosure? I don't know if that's a defined term. Yes. Enclosure is a defined term. The case or housing or apparatus or the fence or walls surrounding an installation to prevent personnel from accidentally contacting energized parts or to protect the equipment from physical damage. See table 110.28 for examples of enclosure types. 110.28. 110.28. Party time, party time. 110.28, 28, 110.28. Where is it at? 110.28 enclosure types. Enclosures, fences or walls covering other than of switchboards, switchgear, panel boards, industrial control panels, motor control centers, meter sockets, enclosed switches, transfer switches, power. So Felix, I think it's because of the language, because they said enclosures, and enclosure is a defined term. It points you over here to 110.28. I think you're not going to be just compartmentalizing within, say, a panel board, switchboard, or anything. It says enclosure. Does the new 2020 code for one throw per enclosure come into effect in this instance? One throw per enclosure. I think you're talking about 230, the 230, 230. Talk about the 6 disconnect rule. No, I think it's related. So here's my thoughts. I didn't even call you Harvey. Here's my thoughts on this. I think it's related, and the reason I say that, what he's referring to, are the barrier requirement, or the 6 disconnect rule, where we have the requirements now that tell us that you have to, and it's 230.71, maximum limit 2 to 6 disconnect means you have separate enclosures with the main service overcurrent protect device in each enclosure. So it's very similar. And here's what happens. Why did we make this change? Why did we make this change? We made the change in 230.71 because we were made aware of a hazard when we required the barriers on the service overcurrent devices. And we had to put an exception for the barriers because we said if you're using the 6 disconnect rule, which means in a panel board with 6 disconnects, you're looking at a bare copper bus and 6 breakers. You can't barrier that off. So we had to put an exception in. But we understood the hazard was still there. So you scratch your head and say, how can I justify, if I have a main, I got to put a barrier, but I have 6 disconnects and I'm staring at bare copper conductors, bus, and there's no protection. Why? Because I physically can't cover it. So they basically said, look, we need to go into 230 and put some requirements for the 6 disconnect rule. They didn't want to remove the 6 disconnect rule. They just wanted to make sure that you had a main overcurrent device in each of those enclosures. So now once we did that, people were saying, look, now you can base your arc flash energy off of the main overcurrent protective device in that panel. And then the engineers were going, no, you can't do that because that line side barrier is just for shock protection, not arc flash protection. Now, it does reduce the likelihood. Think about it. If I have exposed conductors and I barrier them all off, I wrap those puppies, I have a much less chance of causing an arc flash. So, but it's not listed to prevent line side propagation. Once that plasma plume goes, there's nothing that says that that barrier can prevent line side propagation. My gut tells me it will, but I don't have a third party test to show that. So they said we need to do something about that, and that's where we said, look, the best way to do this is to move that overcurrent device into its own enclosure. And now you can A, facilitate establishing an electrically safe work condition, B, reduce the incident energy, taking it from 12.7 down to 0.17, significantly reducing the hazard for the electrical worker. So it made a lot of sense, and that's how we got there. I can't even look at your pay. Okay. All right. So I don't know how do we get to that question? Was it this? A push for separate enclosures for service disconnects and feeder breakers for enclosure will be expensive. I don't know if it'll be expensive. I think because you got to think you're removing an overcurrent device. Yeah, the challenge is you're putting another enclosure, but from what I understand, many of those are already in their own enclosure. So, but I don't disagree that the utility should. So NESC needs to step up to the plate. I think some of the utilities, when they put equipment out there, they need to facilitate that. Help those facilities establish an electrically safe work condition and help reduce the incident energy. And I don't necessarily disagree with pushing states for requirements for the utility to provide secondary arc reduction technologies. That's I think a noble, valid discussion, JW. Absolutely. All right. I am I am at 411. Brian Jackson just put out his 100 Days of Article 100, grounded solidly. You're going to want to check that out. Steve Wilson sent me an email. All right. So I think, and the only other one that I was going to talk about, and maybe I'll end with this, because I did say definitions, and Ryan is doing definitions. I had a recent debate or discussion via email with an individual on a task group about why we use Merriam-Webster 11th edition dictionary as for terms that are not defined in the NEC as the next stopping point for what is the definition of a term. And there are two references. So if you did not know, if there is a term used in the National Electrical Code and it's not defined in the National Electrical Code, then obviously we may want to go to another, like a building code or something like that, because then those are all in the codes and standards. But if it's not a defined term in any of these documents, then our reference is not Wikipedia. It's not Tom's House of Words. It's not the Dimitrovich Vocabulary Dictionary, the DVD. It is Merriam-Webster's 11th edition. And I'll tell you why that's the case. And then we'll end on that one. So I am not going to save my changes. As I said, I wasn't going to do that. I was going to do that. I'm going to discard all of those. I'm going to close all of that. Don't save. Now, what are our references for this discussion? Two things. The style manual. National Electrical Code has a style manual. You may or may not have known that. How do you find it? Go to your search engine and say NEC Style Manual, STYLE-MANUAL, and only one E, Style Manual. 2020 National Electrical Code Style Manual. It was just revised. And if you look in this document, in the scope, now you're not going to find Webster. If you do a search, Control F, and look for Webster, you're not going to find it. Oh, here's what you will find. Look at what it says in the scope. The manual provides editorial and administrative requirements for writing NFPA 70 and 70E, blah, 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 blah. Requirements not included. The NEC Style Manual does not include many purely editorial and stylistic matters, including but not limited to the formatting of tables and capitalization practices. For information on these editorial guidelines, see the Manual of Style for NFPA Technical Committee documents. These documents are formatted differently from other NFPA standards. Examples of these differences include, but are not limited to, arrangement of the document, to its internal numbering system. The National Electrical Code Coordinating Committee staff liaison shall be responsible, blah, blah, blah. And look, they're referencing the Manual of Style for NFPA Technical Committees. So here's what you do. You do Manual of Style for NFPA Technical Documents. C, Control V, Manual of Style. You click on that. There it is. And that is the latest version, 2004. Now, let's do a search for Webster. There it is. Look at that. Where terms are not defined in this chapter or within another chapter, they shall be defined using their ordinary accepted meanings within the context in which they are used. Webster's Collegiate Dictionary, 11th edition, shall be the source for the ordinarily accepted meaning. And if you look in Article 100, I think it is, or is it chapter? This article, that's article. Article 100. Article 100 is definitions. So we got to look at the scope of Article 100. Man, my eyes are going bad. All right. This article contains only those definitions essential to the application of this code. It is not intended to include commonly defined general terms or commonly defined technical terms from related codes and standards. In general, only those terms that are used in 2 or more articles are defined in Article 100. Definitions are blah, blah, blah. So when you get to general terms or commonly defined technical terms, you are pointing basically to the Webster's Collegiate Dictionary 11th edition. So don't go looking in Wikipedia. Don't find a definition that meets what you want it to meet. You've got to use one reference, and that is the Webster's Collegiate Dictionary 11th edition. So if you didn't know that, hopefully you know that now. And now you know why. And it goes back to the Manual of Style for Technical Committee Documents and the NEC Style Manual. So you got 2 documents, and you got to use them correctly to get you over to the Merriam-Webster's Dictionary. All right. So it is well over my 1-hour Q&A Friday. I didn't know what I was going to talk about, but you know what? We got it done. I think we answered some good questions, and we got in deep enough. Hopefully you got something out of today's discussion. And I know I did. Thank you, Ryan Jackson, and a few others for some good questions. So, all right, everybody, safety parameters, safety matters. And remember, have a good day today. Have a great weekend. And please remember all of those that we lost in the trade towers. When our anniversary is September 11th is tomorrow. So say some prayers. And we will probably see you next Friday for another Q&A Friday. So if you got questions, please send them over and all that good stuff. Thank you, Felix, for joining in. And hopefully everybody has a great weekend and great rest of your day. In fact, you know what? Take the rest of the day off. Just anybody ask, if you just say, Tom said it's okay. All right? All right, everybody. I am going to sign off. We did enough damage here today. Nikolai Tesla, have a good weekend. Chris Folan, thank you. Have a great weekend. Smash that like button. Here, you know what? Look, I even got a GIF for it. Right there. Subscribe. Watch. Subscribe. Hit that. Subscribe. IU1141. IU1141. All right. Hit the like button, subscribe, all that jazz. Take care, stay safe, God bless, and remember, please, stay healthy. Be careful out there. Signing off. See you, everybody. Righty then. Need to hit the button.